Hello and welcome here at the Salon Universitas. Actually, also welcome to our beautiful university. Unfortunately, most of you are not able to see this wonderful campus these days. Actually, there is so many things are happening now, and if you wander around here at the campus, you find so many inspiring things, so many projects which are somewhere between art and science, which have very provocative things, and also some kind of really great science projects which are on display here. What is very interesting here is to see all these transdisciplinary works, these transdisciplinary discussions which are led here, which are held here in the upcoming days. And actually this kind of approach towards transdisciplinarity, art and science, and this wider understanding of technology is something what the Johannes Kepler University and the Ars Electronica have in common. And so it's a pleasure to also welcome Ars Electronica here on the campus in Linz. Actually, the big challenges of our time, which we are now facing, if you name it like climate crisis and so on, they all need a certain approach to tackle with these challenges. And one aspect which we believe in is that transdisciplinarity is a key towards these problems or to address these issues. So this is also the reason why the Johannes Kepler University started some months ago with the topic to claim a manifesto in innovation through Universitas, where we actually call for a new transdisciplinary culture in universities. And this manifesto is not only for us a call, it's also a certain mission which we would like to fulfill. And so we thought very much about what can we do to address this, to bring this culture into university, to make projects happening, to foster this discussion. So what we did is once to start, for instance, with University of Applied Arts in Vienna, a special cooperation where we make a call for artists, a call for scientists to work together on new projects. But also we have here on the campus the LIT, the Linz Institute of Technology. And in its founding idea of the LIT, there is this broader technology term in it. And we understand technology not only as a technical discovery, we also understand technology in the sense, what does this technology make to our society, to our economy in a broader sense. And this is how we define technology here, and this is also where a lot of things in transdisciplinary thinking are within. And so we made the decision to make a special call for projects on the edge between art and science, on this theme of transdisciplinarity, and we got a very, very great response. We had I think over 50 applicants, and we have chosen 12 very interesting projects which are on show these days at Ars Electronica. And I'm very pleased that we have today with us 4 of those projects that introduce themselves for a couple of minutes, and to give you a teaser to come here at Ars Electronica to look at them and get inspired. So the first project I would like to call on stage, not only the project, but also the person behind, Alice Hofstetter from the School of Education. And she's introducing the first project. Alice, the stage is yours.
Thank you. Hi, my name is Alicia Hofstetter. I'm representing the JKU Linz School of Education. And I'd like to present our project, the STEAM PopUp Lab, with a special topic of patterns. We created a series, actually a network of online workshops, especially for the occasion of the festival, where we want to showcase different things. So one important thing for us is collaboration between the sciences, because this is not only bringing us forward in reality, in life, also this is something that we believe we should do in school. And we still have a lot of artificial borders between the different subjects. So what we did is that we created this network of workshops where visitors can go through every workshop individually, but they can also jump in between. So one can either do chemistry experiments, one after another, but also watch simulations or watch videos and then decide where to continue from the one that they started with. And some of the workshops that we presented here also happened in collaboration. So for example, the Lichtenberg patterns is a collaboration between biology and physics that shows where those patterns exist. Especially now that a lot happens online and students a lot of times are not able to go to school, we still want to engage people to take things into their hands, to try things out at home, and to really go back to having something in your hand. So this is why, for example, on the origami workshop, we engage people to really take it into their hands, take a piece of paper, create something, and then on the way, learn about patterns, learn about mathematical concepts. So within this workshop, for example, there's also the mathematical part, where you not only create something, but also learn about the axioms of folding origami, and with that, the corresponding mathematical concepts behind it. We also want people to experiment. So we created a series of experiments that you can easily do at home with things that most of you have at home or that you can easily buy. And with those experiments, some of them are easy, some of them are hard. So you can start at the beginning, or if you prefer starting with the hard stuff, you're welcome to do so. Then we also have workshops that allow you to experience. So for example, you can go outside with your phone, with an app, go down a slide, measure what happens, and then play with those values and see what happens next. Or you can go walk through a virtual maze on the grass, which you can also do here on the park. So if you're coming to the campus here at JKU visiting the festival event, then please come see us. We also have this workshop in the park. And of course, we are the School of Education. We will never forget about the learning part. So within all those workshops, it's about having fun, it's about exploring, but of course, it's also about learning. So if you want to see more, and if you're interested in trying it out, then please come visit us at geogebra.org/STEAM PopUp Lab.
Okay, thank you very much for this short insight. Actually, there's, I think, a lot more to talk about. What I would be interested in, I mean, the School of Education here is pretty famous for the mathematical education here. I mean, you have the name also that this is a place where GeoGebra is coming from, one of the most successful tools for in the field of mathematics in schools. And I just wonder, you're working a lot with pattern, with aesthetics, with children, and I wonder if there is any impact which you can measure, which you found out that people get a better access to mathematics with these kind of approaches?
Yes, of course, there's science and research around that topic, but I think it's quite easy to understand that if you can take something in your hand and really explore the reality around it, then it's easier to understand the concept behind it too.
Absolutely. Okay, thank you very much. And I would like to go to the next speaker for now, who is Martina Mara, and she is from the LIT Robopsychology Lab. Martina, please. The stage is yours.
Hi. Common habits these days. Oh my God. Disinfection, taking off the mask. The LIT Robopsychology Lab is a relatively young lab here at the JKU campus. We are trying to combine findings and methods from psychology with upcoming issues on robotics and artificial intelligence. And we are so excited because this Ars Electronica Festival is the very first opportunity for us to present to a broader audience the questions we deal with and how we conduct our research. So for this festival, we've created a whole interactive area which you can find at the LIT Open Innovation Center, and it's called Robots Talking to Me. It consists of various projects, all dealing with question of human machine communication, how we want robots and AI systems to talk to us, what voice we want to give them, and what it takes for us people to trust all these clever machines in our environments. In general, with our research, also with these projects, we would like to contribute a small bit to a more human-centered future of technology. And I think it's absolutely key. It's so necessary that we have transdisciplinary teams working on such a positive future, because we need all their skills. We need the different perspectives of different disciplines. And this is absolutely reflected in the 4 projects that I quickly want to introduce now, and that you can find in the Robots Talking to Me area at the Open Innovation Center. The first project is a virtual reality game called Cobot Studio. Cobot stands for Collaborative Robots, and in this game, by taking on a VR headset, you would meet virtual industrial robots, and together with them you have to sort, pack or paint rubber ducks in a virtual rubber ducks industry hall. What is our research interest when we let our visitors play this game? We want to find out what kind of non-verbal signals of industrial robots are well understandable for their human teammates, and how is this understandability and how is this communication by industrial robots connected to trust or trustful team play with industrial robots. This VR game is created by a highly transdisciplinary team by 7 partners coming from all over Austria, and the disciplines that took part in creating this VR game range from psychology, that's us, and robotics, to game designers, to media arts, to safety, to multimodal communication. The game looks like this. Oh no, there's sound. Could you mute the sound, please? Thank you. Okay, this is how the virtual environment looks like. You will get beamed in this industrial hall, and in this sequence of the game, for example, you have to guess as quickly as possible which target location the robot wants to move to by reading its nonverbal signals. All right. We have a second virtual reality game on display which you can try out in our area, and it's completely different. It's called Serum 13, and in this game you won't meet embodied robots, virtually embodied robots, but you have to cooperate with a non-embodied AI assistant called X21 to solve puzzles, tricky puzzles in a virtual biotech laboratory. Because in this game you have to create a saving serum for a untouched island world and their creatures. So what is interesting for us in this game is that we let the players decide when do they want to trust the recommendations, the decisions that the AI assistant gives them in the game, and when do people prefer to find solutions for themselves. And we're going to find out what factors influence the trust building in AI assistant. This world looks a bit different. You would find yourself in this virtual medical lab. For example, you have to decode X-rays, sometimes by yourself, sometimes with the help of an AI system. You have to get proteins in the right order. This game so far only exists in German. The former one, the Cobot Studio, could be played in English or in German. For both VR games, our visitors would have to register themselves in advance. So please look for Robots Talking to Me on the internet and book your slot for one of the games via the Ars Electronica website or via the website of the Robopsychology Lab. Another project that I really like and that we're going to present the very first time tomorrow is completely different. It's not virtual, it's very haptic. It's called Vote Panels, the future we want. We're going to have 3 wooden haptic display boards around the Open Innovation Center, which invite you as the audience to vote on fundamental ethical questions about the use of robots and AI in our future society. The panels are still in production, but they will be there tomorrow. And you're going to find 3 different questions on these panels and a QR code. You can scan the QR code, and via the app, you can vote yes or no regarding the question you would find on this panel. And the magic part about this project is that in the lower part of our haptic panels, the current mood of the voters is displayed in real time via an LED display and a mechanical mood meter. And this was also a transdisciplinary cooperation with graphics and interface designer Florian Reiche from Germany, currently based in Linz. The last project I quickly want to show you is an ongoing cooperation between the Robopsychology Lab and the AI Lab here at JKU. It's called K. That's referring to Johannes Kepler, and it's our small, cute, interactive robocar. This little car will drive autonomously on changing terrains, and it can already recognize gestures and predict movement patterns of pedestrians. And a part of my lab was that we created an interaction design for this car, and together with designers from Vienna, we've created this interactive LED shell, which you can see in this short smartphone video, which we took last night. Okay. So, come by at the LIT Open Innovation Center and try out all our stuff. You'll find us in the Robots Talking to Me area. Thank you.
Thank you very much for this presentation. I mean, it's obviously, if we look at your project, that you have a big track record of interdisciplinary or transdisciplinary projects, and not only talking about the positive sides of transdisciplinary project. I just wonder, where do you see the downsides, the negative aspects, or the hurdles you sometimes have with transdisciplinary projects?
Okay, of course. I mean, if you're involved and if you have some experience with different disciplines working together in such projects, of course, you recognize that it's actually damn difficult. Because in reality, I mean, you really have to learn each other's language, for example. There are terms that are used completely different in the one discipline than in the other ones. And what else is important, I think, is that we have to probably still come over the stereotypical preconceptions that we have about the others, the other communities. Like some people think that software engineers only think about, you know, creating cool code, but don't think at all about ethical issues. Computer scientists think that psychologists don't have any clue about mathematics or don't understand technology at all. So we have to overcome this. And what we try at JKU, I think, already by, for example, bringing together students from psychology and students from computer sciences is to get them in touch as early as possible and let them learn how to communicate to each other and how to cooperate. I think it's very important that we teach that to young people. Yeah.
Thank you very much for this insight.
Thank you.
And thank you for your contribution. Okay, we are going to the next project. Actually, we are staying in the topic of robotics, a different kind of robotics, more I would say soft robotics from the LIT Soft Materials Lab from Professor Kaltenbrunner. And we have today on stage two people from his lab, Florian Hartmann and Melanie Baumgartner. And please come here on stage with me. And we also bring extra person or an animal in the room, the elephant. So please start with your presentation. Thank you.
Yes, thank you very much for your introduction and giving us the opportunity to present here our project, The Elephant in the Room. So Florian Hartmann and I, we're both from the Soft Matter Physics Division and LIT Soft Materials Lab, and there we work on many different projects. So on the one hand, we do robotics and electronics made of soft materials because we want them to mimic nature as good as possible. On the other hand, we do imperceptible electronics. So these are electronics that are so lightweight, even lighter than a feather. And if you wear them on skin, you do not feel them at all. Another very important topic for us is sustainable technologies. So we are working on a new kind of solar cells, which are very cheap, easy to produce, and with good mechanics. And besides that many different topics, we also have a very international team from many different backgrounds. So we have from people from different areas of physics, different areas of chemistry, biology, mechanical engineering, and the thing that combines us and puts us together is our vision. So we want to create a world where technology, the lines between technology and nature are blurred. So what we wanted is that technology is integrated seamlessly into our everyday life. But when you want such a thing, you always know that there is also a downside. And this is where we come to the elephant in the room. So the elephant in the room is a metaphorical idiom when you know there's a problem, there's an issue, everybody sees it, but nobody is talking about. And when you want to have more technology, more robotics, you always have to keep in mind that this need will produce an enormous amount of waste, very problematic waste. And this is the part where our research begins.
So, in the beginning of our project, The Elephant in the Room, we asked ourselves a simple question. Can we unite high performance and environmental friendliness in a single soft material, and at the same time keep the production and material costs low? And of course, the simple answer, or the short answer, is yes, indeed we can. But it's not always simple when you're doing this. And the full answer we were able to publish recently in the high-impact journal Nature Materials. And this is really a breakthrough in materials research, as we for the first time developed a material composition that unites very important features. We have extremely high stretchability, which we need for soft robotics and electronics that can be attached to our skin. Our material has a very long shelf life and low cost, which makes it attractive for industry. And it's also very similar to our own body, because we call it a biogel. That's because it's biologically derived to 100%, and it's also a hydrogel, a polymer that contains larger amounts of water. And this kind of material is very similar to our own body. We also contain a lot of water. And that gives us a distinct advantage over conventional rubber-like materials, because this water content allows interaction with body fluids like sweat, or we can put dissolved drugs in it and generate the next generation of medical devices and healthcare monitoring. As an example, we developed an electronic skin, a sensor patch that you can attach to your real skin and which measures temperature, humidity, and pressure, just like the functionality you have with your own skin. And this very same material we can use for soft robotics. Soft robotics is a class of robots that mimic nature. For example, the fluent movements of an octopus or fish. And they do this much better than any conventional robots out of metal and electric motors. So for our project, The Elephant in the Room, we did not make any fish, but an elephant trunk. And this elephant trunk, it consists of our biogel. It's a tube which you can inflate, and it has a cotton textile exoskeleton, which directs the movement of this elephant trunk. So if you look at nature and you see an elephant, you have two distinct movements, like this S-shaped lifting movement or a simple U-shaped bending movement. And this we wanted to replicate. In a broader context, of course, you just not want to mimic animals, but think of soft robotics as part of human interacting technology. For example, soft robotic prosthetics or grippers that harvest delicate fruits or produce in general. So what we have prepared for you, if you have the chance to see us here in Linz, is an exhibition where you show you 3 of these elephant trunks which move in these characteristic patterns to music or just as we wish to. And as sustainability is very important for us, we tried to use as much renewable resources and biodegradable materials as possible. So we have lots of wood materials, cotton, fabrics. We have even fungus as a display or construction material. And of course, our biogel, which is used for the elephant trunk. So with our project, we hope that we can show you how the future of technology can be made sustainable. And I would very much like to see you at our exhibition.
Okay, thank you very much for this. Just one question, where is the exhibition placed?
Our exhibition is also in the Open Innovation Center on the west side of the JKU campus.
Okay, and I mean the project and everything what you're doing in your lab is quite inspiring for a lot of people, and you know, Ars Electronica is attracting a lot of designers, a lot of people from industries. Actually, did you already had contact with people interested in this technology, or where do you see, I mean you named some applications before, but where do you see possibilities, or how would it be possible to work with you together?
So, of course, if we combine these actuators and fabrics for prosthetics, you can make gloves that have integrated soft robots, which can help you to lift your arm. Or if we're speaking of interacting with designers and artists, we can also think of gloves that have some movement built in. So not only to display a wearable, but a smart wearable, which has technology as a central part to show it to the rest of the world.
Okay.
Yes, so I also think that maybe people from industry would be interested, because we already tried to really made the best of our biogel, but of course with machinery like extrusion molding, we even would get better mechanical performances. So if there is a company maybe interested, this would also be very interesting for us.
Okay, thank you very much.
Thank you.
Thank you very much.
So we are coming to the next and also to the last project in this slot. And I'm happy to welcome the two people, the brains behind this next project. I mean, one brain is sitting somewhere in, I think, Miami or something like this. We are talking about the Pangolin Project, which is a project which was initiated by the Institute of Integrated Circuits, yes, and g.tec, and we have here Thomas Fassetto with us and Christoph Guger, and they give an insight into this project now. Thank you very much.
So thanks for the short introduction. Today we're here to present our project Pangolin Scales, which is basically a combination of a PCI interface and a robotic stress. So Christoph, can you tell us something about
brain-computer interfaces are used for many years at the Ars Electronica Festival. Here on the image you can see, for example, a project where Dragan Ilic hooked the brain-computer interface up to a robotic device, and with mental activity they could design drawings. And on this slide you can see an example of the Cybertron. So this is like the Olympic Games for paralyzed people, and they can use the brain-computer interface to drive a wheelchair. There was just 3 years ago the last Cybertron. I have to go back a little bit. Sorry. And brain-computer interfaces are used also in medical applications. So in this case, for example, neurosurgeons are implanting electrode grids directly on the cortex. For that you need a neurosurgeon. They remove the scalp and then they place the electrodes directly onto the brain. And this is a very good chance for developing brain-computer interfaces. And here in this video you can see an epilepsy patient who has 256 electrodes implanted. And the brain-computer interface is analyzing hand gestures. So on the computer screen you can see that the instruction is to make a peace sign. The patient makes the peace sign, and then the robotic hand is controlled with the brain-computer interface, and it's copying the behavior of the patient. But this experiment is only possible if we are implanting the electrodes directly onto the cortex, and this is pretty invasive, so you always need a neurosurgeon for that. And we also wanted to do it non-invasively. This means directly on the head without a neurosurgeon. And this was inspired by the pangolin. So you can see the animal has a lot of scales. And for that reason, we designed EEG electrodes that look like the scales of the pangolin. And one of these grids holds actually 16 channels. And when we place 64 of these grids on the human head, then we can read out 1024 EEG channels with a never-seen resolution before in brain imaging. Please go ahead.
So thanks, Christoph, for the introduction of all the possible applications. And for many of those applications, definitely there would be a benefit if the EEG signal, so perhaps we can stop the fast-flowing animations there. It would be definitely beneficial if we would be able to wirelessly transmit the EEG signal, and that's where our science, the Institute for Integrated Circuits comes in. So we have managed to more or less compress all the standard electronics needed for the EEG signal recording and added a further layer of wireless communication to it. And here we see a photo of the model where we placed our wireless EEG electrode on top of her head. We have there the EEG sensing grid directly mounted on the skin. And then we have several layers of PCBs where we at the moment have some configuration other interfaces there. And on the top PCB, we have mounted basically an antenna and our microchip that does all the magic. So for future applications, we will be definitely able to realize a system like that we see on the right side of the slide. So we basically only would have an antenna that will transmit the information signal of the EEG signal, and we have the signal, also the system on the chip that is basically all the integrated electronics there. So what's inside such a system? So I really do not know how this now all happens, but we can jump back. So the standard EEG system, it more or less tries to record an electrical voltage that is collected from an electrode. We do that also in our integrated circuit. We amplify the signal, we digitize it using a custom-built analog-digital converter, we do some DSP processing, and finally we transmit the recorded data using a customized RF transmitter. We're using an antenna also for future applications for harvesting the supply voltages and the supply power basically for all the blocks. So we generate the electrical energy basically from the field surrounding our transponder electrodes. That's called power harvesting. To give you an example, we are harvesting a power in the order of 5 to 10 microwatts there. And with that amount of energy, basically all the system blocks are working. And the magic is to give all the functionality with this small amount of power. And that's where our research, the integrated circuits, come in. I have presented here some block diagrams of the circuits. We see the transmitter, the power harvester, and so on. And basically also we do not use simple resistors because of constraints in the area. We're using switched cap circuits, for example, to replace a simple resistive element. And we're doing much more tricks to get rid of the power constraints and also to deliver the performance there. The final realization will look like that. That's the so-called layout view. We have made a chip photo there within an area of around 1.5 millimeters squared. We have there the ADC and all the things here more or less painted in yellow and green. So here on this slide we see our model when we did the first prototyping test. The JKU electrode is placed on top of her head, and that is surrounded by all the electrodes connected with the cables to the g.tec system, where g.tec provides then the BCI signal processing and so on.
And then we had Anouk Wipprecht, who designed the Pangolin Dress with several actuators, so there are servos inside so that the scales can move, and we have also lights inside that can blink and flash. And this is all controlled with the brain-computer interface, and we can calibrate the brain-computer interface on different tasks, and the dress is actually afterwards reacting to it. And one task is, for example, to recognize Gerfried Stocker. And when the model sees Gerfried Stocker, the brain-computer interface recognizes it, and suddenly all the scales are moving. And Anouk made also a very nice video, which is already online, where you can see how the dress is reacting to brain waves.
So perhaps you can now switch on the audio for the audience. This is Anouk, by the way. So basically, Pangolin Scales is a BCI system that uses this Pangolin scale stress to visualize the EEG recorded data. So the stress reacts directly on the signals that are recorded by the BCI system. And that you will see in the Learning Center. So I want to thank all the partners. Anouk could not be here today. I want to thank g.tec and also the people from my institute. We developed the integrated circuits for the project during the last 4 years, and many people were involved there. I just want to mention the last project partners, Professor Harald Prettel, and also Stefan Schmickel and Patrick Vater. So thanks.
Thank you very much.
Okay, thank you very much. I mean, you were talking before, Thomas, about the wireless version of it. So how far are you ahead or behind, or what is the plan or time frame?
As we have seen in the block diagram, all of those blocks are basically available and they are more or less functional. So all is ready, but the last steps are to do. So the industrialization, let's call it that way, that has to do. And I think the path to go there, especially for the large amount of channels. At the moment, we are having just a few of them. One of those grids has 16 channels. So we want to do a whole of the 1,000 channels doing the wireless thing, and also trying to not use, for example, external buffering batteries and so on. So I think we are at around 85% of the project, I think. So it's quite far, I think.
Super, great. And Christoph, to you, I mean, actually it's not the first collaboration with Anouk. I think it's the second one. I'm not sure if there had been something in between. I just know about one. And I just wonder, when you worked first with her or with designers, I remember you had been a little bit skeptic at the beginning, but what changed, and what changed in the collaboration, or what is the benefit for you also as a high-tech company to work with designers and so on?
No, we were not skeptic against Anouk. We just have so many collaborations that we have to be picky, because we have limited resources. But Anouk is very unique in her dresses that she is designing, and she understands very well the technical side. So it's very easy to interface engineers with her skills. So for us, it would be impossible to design such a dress because we are limited brains engineers. And you need a fashion designer like Anouk to put it into a good-looking piece of work. So we can solve the engineering part, but you need Anouk so that it's good-looking and sells well, very well.
Okay.
And I can also comment on that. Anouk really helped us to understand all the parts of the project, also her part of the artistic things and so on. And she really had an open ear for all our problems. So thanks again, Anouk, if you hear us.
Yeah. So super, thank you very much. And it's also great that we had this last project where there had been so many, first of all, a great project outcomes with all dimensions, with a great scientific outcome, a great artistic and design project, a project where everybody involved learned a lot out of it. And I'm very happy that these projects are on show here on the campus, but all the 4 projects you have seen, they are just 4 out of 12, I think. There are many more to discover, and so please keep your eyes open, keep the streams on, come here, look at the project. There's a lot of inspirational things, and it was a pleasure for me to welcome you here in this little panel, and have a nice day, and see you hopefully soon at Ars Electronica.